We're going to go over the basic concept of a horizontally fired projectile. One of several cases of motion in two dimensions we're going to get into in Chapter 3. So just as a simple scenario, we're going to have a ball rolling off a tabletop horizontally and following a projectile trajectory that's parabola-like. So we're going to note a couple positions of what we could take from a general situation like this and then apply it to more complex situations. Alright, so number one, this vector arrow I have drawn represents the horizontal velocity the ball is traveling at on the tabletop. When it rolls off that tabletop, it will continue with that same horizontal velocity, assuming air resistance is negligible, until we hit the ground down here later. So we are going to just simply label initial or velocity on the x-axis as Vx. But as a matter of fact, I'm not even going to use the initial symbol because it will stay and maintain that the whole time. So it's actually constant. And to begin with as well, while it's on the tabletop and the moment it rolls off, our initial y velocity, if it's a horizontal projectile, is equal to 0. We'll discuss more about that y and prove y in class. But basically, as it's rolling along the tabletop, obviously it has no y velocity, and it won't until it rolls off and gravity begins pulling it down. Essentially, it's just the same idea as when something is in free fall and is dropped. We said the initial velocity was 0. Same here. But this will change and this one won't. So let's take a position later on of the ball. Let's say maybe right here. We'll just put a dot there representing when the ball gets to here. When the ball gets to here, we still maintain the same exact velocity that we had horizontally. So whatever Vx was to begin with, we'll draw the vector arrow. Oops, I should draw it a little bit longer. We'll draw the vector arrow roughly the same length as it was to begin with. Looking a little bit short there. Let's make that a little longer so it looks like the other one. Alright, so that arrow and that arrow are about the same size, meaning that the x velocity still is and is constant what it was to begin with rolling on the tabletop. But obviously now gravity has taken a hold of it, and we have a y velocity pointing downward that is not 0 anymore because of g. Once it's rolling off the table, we know from free fall g equals negative 9.8 meters per second squared the whole way down through this trip as long as air is negligible. So now we have a Vy final at that moment that's non-zero. What it is depends on how far or how long it fell at that point. So let's pick another point, let's say a little bit further down the road over here. And we still have a Vx that's the same value that we began with. Same value here, same value here, same value here. Projectiles will travel horizontally at a constant rate the whole time until it hits wherever it's going to hit. Again, as long as air resistance is negligible. You have a lot of drag on it, then that will slow it down, but we're going to ignore air resistance. Now, compare this position now to this one. Vy was 0 to begin with. Now Vy has some negative value pointing down, and now it's going to be even more negative because gravity had longer to affect it, or acceleration due to gravity. So as we go down, it should be kind of obvious that this will grow, this will stay the same until eventually it hits the ground down here, and the Vy will be at its max the moment it strikes the ground. So that's pretty much the gist behind the basics of horizontal projectiles. We'll discuss the equations in class, which turn out to be just ones we've really already have used. And next we will go on to projectiles fired at angles.